Hello, ME452. This is Evan speaking for Team 4. I'm here to show you what Amelia, Assad, Gihan, Jason, and I have done for our project. Alright, gonna just briefly go over what we went over in our interim presentation. As you can see here, we have a lovely rendering of our espresso machine, thanks to GrabCAD. These espresso machines are used all over the place, really, in homes, offices, coffee shops. Some small businesses use them to treat their employees and their customers. They're a lot different from regular coffee makers that you might have in your home because they produce a lot stronger form of coffee by pressurizing the water at a precise temperature, running it over the finely ground coffee. There's a lot of key components that you can see here in the rendering, such as the bean storage, the water reservoir in the back. There's a control panel and a steam wand to heat up your drinks. The total amount of units we expect to sell is 550,000. And here we have the exploded view of the CAD that we initially borrowed, showcasing some of the components that we focused on for the redesign. I got the water tank in the back, the bean hopper up top. I got the front control panel all there that you can see all separated out. And here we have our consumer groups, the primary of which is residential use in the 35 to 60-year-old age range. We have a little bit higher age range because the price range is higher on these devices. The secondary consumer group is smaller office spaces, maybe something like a hair salon. It's not quite Starbucks level, but the commercial version will put out the quantity needed for those kinds of spaces. And here we have our fast diagram. You can see the task function is to brew the espresso. There's 4 primary basic functions: pressurizing water, grinding beans, heating water, and dispensing espresso. Pressurize the water by pouring water and increasing the pressure of the system. You then grind the beans by storing the beans and rotating them. Heat the water by storing the water and adding heat. We need to assure dependability by controlling the temperature and preventing burns by maintaining the control and guiding the pouring of espresso. You dispense the espresso by dripping water and filtering the espresso beans. We need to assure convenience by making the settings adjustable and allowing hands-free operation. We enhance the product by controlling the pressure, frothing the milk, and brewing espresso quickly. Finally, we need to please these senses by adding a variety of colors and including accessories. This is the function component mapping matrix. The matrix relates the components listed in the bill of materials to the basic functions listed at the end of the fast diagram. We see a difference between components that serve one purpose and those that serve multiple functions. For example, the lower shell is used to add colors, while the front panel helps to control temperature, adjust the settings, and include accessories. Having multiple components that serve the same function tells us the importance of each function. And here we have the functional comparison for our product family design. As you can see, the functions of storing the beans and storing the water are the only differences between the consumer groups. And accordingly, the water reservoir and the grinding cradle are the modules that change from one platform to the other. And here's a couple assembly sequences. As you can see, we improved this assembly sequence greatly, delaying the differentiation of the assembly by moving the modules to the end of the assembly sequence, the water reservoir and the grinding cradle. Here's a spreadsheet that looks at our design for manual assembly analysis, looking at the insertion and handling time for each part. In total, the operation time came to 120 seconds. We also calculated the manual assembly efficiency, which came out to 27.5%. The parts highlighted in green have high operating times, and we will be redesigning these parts to reduce operation time and increase manual assembly efficiency. The first changes we focused on making were adding snap fits for various panels to greatly reduce the total assembly time of the part. This also increases the accessibility of disassembly and performing repairs for both the consumer and the manufacturer. Let's take a closer look at the front panel. By changing it to a snap fit design, we are increasing ease of assembly and decreasing screw count, which follows DFA 1, 2, and 3. For the module part, we had initially created a reservoir suited to the secondary consumer group by increasing the size and adding a handle, but the design can be further improved. Changing the shape of the water reservoir allows for easy orientation with an added plane of symmetry. The final Reservoir redesign is even bigger to serve more customers and features two handles on opposite sides of the tank, so it's easier to carry and assemble, even with the extra capacity in the larger product variant. Its new shape allows it to be connected to the rest of the machine through only the bottom without fear of tipping over. And here you get a look at our analysis for the redesign for manual assembly. With the addition of snap fits and the reduction of fasteners, the operation time for the recessed panel assembly was halved. The total operation time for the front panel was also decreased. As you can see, the total operation time is now 102 seconds, a reduction of 18 seconds from the original design. The manual assembly efficiency also increased by approximately 5 to 32%. We also analyzed the front panel subassembly to determine its viability for automated assembly. We analyzed the orienting efficient relative handling cost and feeding cost, as well as the insertion cost to determine the total assembly cost for the automated assembly. We found the total assembly cost to be $7.26 for automated assembly. The front panel subassembly contains many different valves, tubes, and buttons that can benefit from automated insertion. However, the geometry of the panel is very complicated, so we can optimize it for automated assembly by splitting it into two pieces and redesigning them so the valves, that is the portafilter, grinder output, etc., can be easily automatically assembled by a machine. The bottom panel is then joined with the front panel and manually assembled with a snap fit shown earlier. This reduces operating time, part complexity, and assembly cost. Our focus for this redesign is on the bottom plate, which contains circular cutouts of different sizes for the valves that comprise its symmetry. The size and position of these cutouts have been adjusted so that the part now has both X and Y axis symmetry, making it very easy to orient. The ends are then curled to prevent overlap during automated assembly. This redesign also required changing the tamper and hot water outlet so the cutouts on the previous slide can be symmetrical. This involved altering the diameters of the handle of the tamper and outer diameter of the outlet to be identical. These changes are shown along with an overhead view of the plates. And here you can see some of our analysis for the automated assembly redesign. There are now two sub-assemblies to make this part the most conducive to automated assembly. The top chart analyzes the redesigned bottom front panel part and shows that it has a total assembly cost of $2.50. The top front panel has an assembly cost of $1 after redesign. The total cost for the assembly of these two sub-assemblies is $3.59, yielding in a reduction of cost in $3.66 because of the redesign. Here you can see our process selection for the front panel. We chose sheet metal forming with low carbon commercial steel, weighs 269 grams with a thickness of 1 millimeter. Here are some of the key dimensions for the front panel. Here's a table analyzing the processes compatible with the material. As you can see, sheet forming is the only viable option for us. And here you can see we picked injection molding to manufacture the water reservoir. It has a thickness of 2.5 millimeters, and we chose ABS as the material. And some of the key dimensions from the CAD of the water reservoir. And here's our process selection table for the water reservoir. As you can see, all of the processes compatible with the material fail except injection molding. And here we list off some of the key features of the redesign of the front panel. When we calculated the manufacturing costs from the design for automated assembly, we can see that before DfM, there was an overall higher cost per part for the material, operating, mold, and total costs compared to after DfM. And as you can see here, after DfM, our cost per part did go up a little bit, although we greatly increased the volume and the symmetry and the ease of handling for the part. Here we have an overview of our service system, pretty comprehensive, including a 1-year warranty, an option to extend it, a return policy. We also chose some e-copies of our books for environmental impact purposes, along with the Sustainability Committee. And here we share some of our concluding thoughts on the project. Some of the key improvements were cost reductions and increase in capacity. Some of the design highlights were removing fasteners, We didn't get around to an ergonomic study, and some of the future refinements we want to make is an iteration of the front panel and recyclable material use. And that's all from Team 4. Thank you.